This is page 247. We're at the bottom. We left off on number 16. So this video is actually going to be the bottom of page 247. We're going to do pages 247, just the bottom of it, and then we're going to continue on and do 248, most of it. All right, check out number 16 with me. I'm going to use a whiteboard here to do my ladder diagram. Number 16 reads, the number 2 is chosen to begin a ladder diagram to find the prime factorization of 66. What other numbers could have been used to start the ladder diagram for 66? I'm going to stop reading right there. We're going to answer the second question in a minute. Let's go through and answer the first question first. So they're saying that we're doing 66 and that we're doing a ladder diagram, so that would look like this. And they're asking if there's other ways we could do 66. And the rule is that if we can factor out a prime number, then we can start with a different number besides 2. For example, does 3 go into 66? It does. 3 is a prime number that goes into 66. Is there any more? Some kids here would say 6, but this doesn't work because while 6 is a factor of 66, it's not a prime factor of 66. 6 is a composite number. So I have to undo that. 6 doesn't work. But what does work is 11. Now those are the only options. Now let's go through and finish these. Go back to the beginning. 2 goes into 66 33 times. 2 does not go into 33, so I need to find a different factor, like 3. 3 goes into 33 11 times. 11 is a prime number, so 11 goes into itself, and I get an answer of 1. My answer is 2, 3, and 11. I'm going to highlight those. And I'm going to do this one now. 3 goes into 66 22 times. 2 goes into 22 11 times, and 11 goes into itself once. I get 3, 2, and 11. And 11 goes into 66 6 times. 2 goes into 6 3 times. 3 goes into itself once. I get 11, 3, and 2. So let's go back and answer both questions. The first question was, what other numbers could have been used to start the ladder diagram for 66? 3 or 11 could also be used. Now, if you're wondering why I don't mention 2 here, it's because they told us we started with 2. So when we started with 2 here, that was in the directions. We had to figure out, could we start with other numbers, and we chose 3, and we chose 11. And the second question is really interesting. It says, how does starting with a different number change the diagram? So do you notice that the prime factorization in this first one is 2 times 3 times 11? And the prime factorization in the second one is 2 times 3 times 11. And in the third one, it's 2 times 3 times 11. Now the diagrams look different, but the prime factors are all the same. So how does starting with a different number change the diagram? It changes the order of the prime factors, but it doesn't change the prime factors. Starting with a different number changes the order of the prime factors, but it doesn't change how do we say this? But we still use the same, we still get the same prime factors. We still get 2, 3, and 11, it's just a different order, and that's no big deal. Alright, so that answer looks kind of funny because we hand wrote and we typed, but that's okay, it's no big deal. Alright, let's move on. Let's check out number 17. Number 17, critical thinking. List 5 numbers that have 3, 5, and 7 as prime factors. So this one seems a little bit tricky, but let me show you how it's really not. So if 3, 5, and 7 are the prime factors, what that could mean is that we end up with like a factor tree that looks kind of like this. 3, 5, and 7. I'm going to go like this and put 15 here and 7 here. 7's prime, 15's not, and I get 3 and 5. So what's that number though? Now let's see if this makes sense. I'm using these 3 numbers right here, 3, 5, and 7, and those are the prime factors. So I've got 3, 5, and 7 right here. I want you to pay attention to how I got this set up this way. All I did was I multiplied 3 times 5 to get 15 right here. And then I used 7 from my prime factor list and put it right there. That's prime. 15's not, so I broke it down into 3 times 5. What is this number right here? Well, it's 7 times 15. It's 105. 15 times 7 is 105. So one number that has prime factors of 3, 5, and 7 is 105. What about the next number? Watch how easy this really could be. What would be another number that these would all be prime factors of? How about just this right here? Times 2. So what am I doing here? I'll show you what I'm doing. I'm going to do 3 times 5 times 7. That's 105. And then I'm just going to multiply that by 2. I get 210. And so I'm going to actually check that real quick before I write that down as my answer. What if I started with 210? What would my numbers be? Well, I know that 3 goes into 21 7 times, and if I annex that 0 there, it's 7d. And I know that 7 goes into 70 10 times, and I know that 10 is 2 times 5. Look at these numbers. This is super interesting. 3, 5, 7, and 2. Do you notice that? 3, 5, 7, those are the three numbers, and then a 2. So what am I doing here? What's my strategy? Well, my strategy is that they give me three prime factors, 3, 5, 7. I multiply them together, I get 105. The next number up would be 3, 5, 7. 3 times 5 times 7, that's 105. If I just times that by 2, I get 210. Or what I could have actually done was I could have done 3 times 5 times 7. Instead of times 2, I could go times 3. What would that be? Now this is going to be really interesting. 3 times 5 times 7. We know that's 105. If I multiply that by 3, I get 315. You should notice a pattern here. My first number is 105. My second number is 105 plus 105. My third number is 105 times 3. It's a perfect pattern. I just add 105 each time. And it's because 3 times 5 times 7 is 105. So two more answers that would have 3, 5, and 7 as their prime factors would be 420. And I could prove that. And 525. I could prove all of those. We're going to stop. Well, we're actually not going to. We're going to carry on to the next page. We're done with page 357. We're going to go on to page 358. It's 200. I said that terribly wrong. We're done with page 247. We're going on to page 248. And we're simply going to start on number 18. Number 18 is terribly confusing, but the math is not too hard. I'm going to help you with it. Number 18 reads, in a game, you draw a card with 3 consecutive numbers on it. You can choose any one of the numbers and find the sum of its prime factors. Then you can move that many spaces. You draw a card with the numbers 25, 26, 27. That's what this means right here, 3 consecutive numbers. 3 consecutive numbers means 3 numbers in a row, 25, 26, 27. And then what we're going to do here is we're going to, this is the math. You can choose one of the numbers and find the sum of its prime factors. So to find the prime factors, we can do factor trees. So the factor trees for 25 would just be 5 times 5. 5 times 5 is 25. 26 would be 2 times 13. And 27 would be 3 times 9. And 9 would break down into 3 times 3. Those are all prime factors. Every number I circled there is a prime factor. What does this mean right here? Find the sum. That means add. So once I find all the prime factors, now I add. Sum means add. So the prime factors of 25 are 5 and 5. If I add those up, I get 10. If I add these up, I get 15. And if I add these up, I get 9. Which one should I choose? You should choose 26. Because its prime factors are 2 and 13, which has a sum of 15. So you would get to move 15 spaces. There's a lot working in that problem, and it's really pretty tricky, but the math wasn't crazy hard, but there was a lot to think about there. Let's move on. Let's just see how much we can get done here. We are on number 19. It says, explain the error. When asked to write the prime factorization of the number 27, a student wrote 9 times 3. Explain the error and write the correct answer. Well, this is true that 27 equals 9 times 3. It's not untrue. If you're thinking to yourself, well, yeah, 9 times 3 is 27. That's true. But the problem is this word right here, prime. Are all these numbers prime? 3 is. But is 9 prime? It's not. 9 breaks down into 3 times 3. The prime factorization of 27 is not 9 times 3. It's 3 times 3 times 3. The student wrote a factor pair, but forgot that 9 is not prime, the prime factorization of 27 is 3 raised to the power of 3. And if you want to just write that, I can't type that in so good, but if you'd rather write this, you could type this in as 3 to the 3rd power. Okay, moving on. Good work. All right, number 20. These are the hot questions, and we're going to try at least a couple of them. Number 20 reads, communicate mathematical ideas. Explain why it is possible to draw more than 2 rectangles with an area of 36 square units, but it is not possible to draw more than 2 rectangles with an area of 15 square units. The sides of the rectangles are whole numbers. So let's start with 15. What could we draw to make an area of 15? Well, we could draw a super long and skinny one. And this would be 15 by 1. Or you could draw a little bit shorter one, and this would be 5 by 3. Both of those statements are true. 1 times 15 is 15. 3 times 5 is 15. Now what could we draw for 36? For 36 we could draw a super long skinny one. That's 1 times 36. Or we could draw a 2 times 18. That's 36. Or we could draw a 3 times 12. That's 36. Or we could draw a 4 by 9. There's all sorts. Well, how come that's true? Well, what we need to notice here is that 36 has several factor pairs, including 1 by 36, 2 by 18, 3 by 12, 4 by 9, and even 6 by 6. Some kids would argue and say that's a square. Well, a square by definition is a rectangle, so it's okay to have a square. While 15 only has 2 pairs of factor, including 1 by 15 and 3 by 5. Part of that, we don't really need to include this in our answer, but part of the reason for that is that 36 is even and 15 is odd, and even numbers are divisible by 2. And when numbers are divisible by 2, they're often even divisible by 4. Notice that we've got a 2 by and a 4 by in this one, and with 15 it's just an odd number, and odd numbers aren't divisible by 2 or 4. So that's actually another actual reason for it. Okay, we're going to see here if we can squeeze in one more problem. We have 1.5 minutes left on this video before we're going to run out. We're going to skip number 21 altogether. We're going to go to number 22. Number 22 reads, look for a pattern. Ryan wrote the prime factorization shown below. If he continues this pattern, what prime factorization will he show for the number 1 million and the number 1 billion? I want you to notice something here. First of all, the first statement is just simply true. 10 is equal to 5 times 2. 100 is 2 zeros, and it's 5 and 2 to the 2nd power. 1,000 is 3 zeros, and it's 5 and 3 to the 3rd power. The next one would be, this isn't part of our question, but the next one would be 10,000 to the, it's going to be 5 times 2 to the 1, 2, 3, 4 zeros, so it's going to be to the 4th power. So the actual question here is to the million and to the billion. Well, a million is a 1 with 6 zeros. So that would be 5 times 2 to the, well, it's 6 zeros. That means it's going to be to the 6th power. And a billion is 1, 2, 3, 4, 5, 6, 7, 8, 9. It's going to be 5 times 2, and each of those to the 9th power. All right, good job. We cruised through page 248. You're done with that page. Great work.